Well, hello everyone, and welcome to this wind power engineering development webinar, Eliminating Encoder Failures in Wind Turbines. I'm your host, Paul Dvorak, editor of Wind Power Engineering and Development magazine. Thank you for joining us. Now, just before we start, there's a brief agenda before I introduce our speaker. The webinar will be available at windpowerengineering.com, and a link to it and the slides will be emailed to everyone who is registered. At the end of the presentation, we'll have a brief question and answer session. Of course, not everyone that could wanted to attend today's webinar could be here, but you can help them learn from it by tweeting the key points and takeaways that you think important. In your tweets, be sure to include the hashtag WindWebinars. After the presentation, I'll read the questions that you and the audience have submitted. And you can do that by typing them into the questions box on your GoToMeeting panel that should be to the right of your screen. Now, if you don't see a GoToMeeting panel, look for a small red arrow in the upper right corner of your screen. Pick on that red arrow and that should release the panel in the question box. Now, I'd suggest that you're not waiting to the end of the presentation to form your questions, but type them in as they come to you and we'll try to answer as many as possible before the hour is up. Now let me tell you a little bit about our speaker. Brian Winter. Mr. Winter is an experienced industrial controls engineer with over 25 years of direct hands-on experience with encoder and motion control applications ranging from ounce-inch servos to 5,000 kilowatt generators. He's worked in the marketing and application engineering roles in IBM, General Electric, Molex, and he's currently employed with Avtron Nidec Automation. Brian has a Bachelor of Science in Electrical Engineering from Rensselaer Polytechnic Institute, and he's a senior member of IEEE. And with that, Brian, the microphone is yours.
Well, thank you, Paul. I'll try to live up to that introduction. So let's start with the basics. Our goal here is to talk about how to help you improve wind turbine uptime. And that sounds like a very simple goal, and it is in an overarching sense. And then we're going to focus specifically on exactly where encoders and feedback solutions fail you in the wind turbines and talk about some specific solutions that we can talk about. Some of these will be more focused on the design end about what could be done in terms of component selection or implementation. Others are more focused on the maintenance and support end. So they're obviously in the ongoing life of the turbine. So we'll try to cover all these areas as we go along here. All right, looks like I should have control of the presentation, and I do. So before we talk about wind turbines, let's just tell you a little bit about Nidec Avtron and why we think we're qualified to talk about this industry. We're founded in 1953 in Cleveland, Ohio. We presently have 2 manufacturing plants still located near Cleveland, but we do have a global customer base. We travel around the world serving wind turbine customers in Germany, all of Europe, North America, China, India, and many other smaller installations. We are part of a $9 billion worldwide corporation. Many of you may know the Avtron name as a small independent company, and we were acquired by Nidec, who's a $9 billion publicly traded company. We are the world's largest producer of heavy-duty encoders for the wind industry. So we think that gives us some pretty good experience in understanding about this. But a lot of what I'm going to say today is not a pitch. It's not a direct talk about Avtron encoders. I'm more going to try to give you generalized ideas and helpful solutions. These apply really to any brand or any type of encoder. So how do we get there? Well, first we're going to talk about the basics of wind turbine applications. Then we're going to talk about each one of the specific applications that employ encoders typically in a wind turbine. And that includes the blade pitch control system, the slip rings, the generators. There's also a couple other applications that are sometimes use encoders, but not as frequently, so I won't focus in on those as much, but if you are interested in those applications, we'll also talk about yaw controls, anemometers, and wind direction indicators. We'll also talk about optical versus magnetic encoders because there's a lot of different technologies in the market. And I think it's helpful to kind of look at the 2 or more technologies available to you. Again, Avtron makes optical encoders. We make magnetic encoders. So we try to explain the pros and cons of each of these types of systems in a balanced way. We'll talk about maintenance tips, and we'll talk about how can you improve reliability. And then as Paul talked about, we're going to take questions. But again, as Paul indicated, we encourage your questions on an ongoing basis. So let's start. Here's a cutaway typically of what you see going on in a conventional wind turbine. And this is the type that you see at a 1.5 megawatt or smaller, or even some of the 2.5 generator styles, where you've got a main shaft coming down from the nacelle. You're turning that shaft through a gearbox, and that drives a doubly fed induction generator. Obviously, for larger wind turbines, some of you may be familiar with the concept of direct drive, where that shaft feeds directly into a very slow turning direct generator. A lot of what I'm going to talk about is still applicable to that method, even if you don't have the gearbox driving the generator. You also see at the front nose cone a sample of one blade pitch control. There's obviously 3 in most typical systems. There's a slip ring, and the slip ring typically has an encoder on it to indicate the position of rotation of the blades. Some vendors use those for calculating position of the blades, actually doing live real vectoring of the blades. Others use it more as an indication of overall shaft speed. You also see the yaw drives there, shown here with encoders on them. Often something less than an encoder is used here, gear tooth counters or proc switches. Then you see the anemometer, the wind vane, so that you can yaw into the wind. Probably one of the most critical things about encoders in a wind turbine is there is no redundancy. If any one encoder fails, you can stop the turbine. Blade pitch, slip ring, electrical generator controls, if your yaw controls fail, just about anything there, it's not a redundant system. And so that's why we're really focused on trying to help you reduce wind turbine encoder failures, because we know for every single encoder failure, you've got a wind turbine failure. You've got a generator sitting out there worth millions of dollars that the customer is expecting to be generating electricity from, and they're not getting that expected return on investment. Or maybe you are that end user and you're looking at your wind turbines like a wind farm that I visited in China, and they said they had a big panel full of TV screens all the way across the wall showing little outlines of wind turbines, and a lot of them were red. And I said, well, this is pretty serious, you know. He said, oh, that's typical. And I said, what's typical? He said, oh, about 15% of them aren't running. And I said, really? And he said, yeah, we have a lot of encoder failures. And I was astonished that here was a guy sitting in a control room hundreds of miles away from any wind turbine who didn't get involved with the detailed control systems, but he knew what an encoder was and how serious it was to his wind turbines. And that's what kind of woke me up and said, this is a very serious issue, and Avtron can help. So let's talk about blade pitch control. Obviously, losing blade pitch control can expose the tower to the extreme wind force. You know, everyone's seen probably that Dutch film where the tower spins out of control and the blades explode at spectacular supersonic speeds. Here's some more serious damage where towers were knocked down. The basic problem here is if you don't know your blade, where your blades are pitched, you've got a lot of force on the tower. So either excessive wind, or if you are trying to service the tower, you lock the generator shaft. You've got serious risk if you don't know that your blades are fully pitched to the safe position where no wind force can pressure on the, no significant wind force can push on the tower. So with that, let's step into what actually goes on in electric blade pitch controls. Here you're looking at a picture where the blade has actually not yet been assembled, so it's going to be attached by those multiple bolt holes around the perimeter. And you see inside, this particular design actually jams all the controls inside the nose cone. That's not always true. Some manufacturers instead put the drives back in the stationary part of the tower, and instead may run slip ring controls for that. But here you see a pitch blade drive, a controller, and then to the right you see the brake, an encoder, and motor. Now this particular assembly is using what we call a motor encoder brake sandwich, and it's got some particular advantages we're going to talk about a little bit later. There's lots of other ways to control and sense blade pitch. This is the type where you're behind the motor with an incremental encoder. So let's talk a little bit about these different types and their pros and cons, their merits, and so on. I'll go back to this picture of the design so you can understand it more clearly. One option is you can put the encoder behind the motor. You can put either an incremental encoder or you can put an absolute encoder back there. We'll talk a little bit about the differences between incremental and absolute a little while later in the presentation. But suffice it to say, they can both mount behind the motor. Or you can instead mount an absolute encoder directly on a small gear that runs off that main gear. You can actually see that big gear in the picture. So some vendors have instead chosen to take a small shafted encoder. Typically they put a big plastic gear on it and then run off the perimeter of that pitch drive. So there's different approaches here that result in the same output, which is you're controlling the blade and getting feedback from the encoder. One important point that I make is that most blade pitch controllers can accept any of these systems. The vendors that have designed these blade pitch machines have designed them so that they can work with encoders behind the motor or directly on the blade. They've designed them so they can work with incremental or absolute. So let's look at what's an absolute versus an incremental encoder, and I apologize for those of you that are encoder experts that already know this. Absolute encoders are really like a clock, and incremental encoders are like the ticking of a stopwatch or ticking of a clock. By that I mean absolute encoders output a complete position. You actually get a little digital message from them periodically that tell you exactly where you're at. So if you're rotated to 10 degrees, you get 10 degrees, 10 degrees, 10 degrees. Incremental encoders instead make pulses as you turn the shaft, and every pulse is the same. So unless you know where you start from, you need a home reference position so that you can move and then count positions to reach, okay, I've calculated, I've moved this many counts, therefore I've moved 10 degrees. So why do we think that picture I showed you earlier of the motor incremental encoder solution is so great? Well, number one, absolute encoders are generally much more fragile than incremental encoders. Most absolute encoders are optical sensors. We're going to talk about the vulnerabilities of that later. They have glass discs. They have plastic gears. They have very small signals generally. They're just mechanically less durable. So incremental encoders on the other side, you can use an optical or a magnetic. You don't have to use a glass disc. You don't have to use gears. So the disadvantage of the incremental encoders, you've got to have some way of finding the home position or going to the home position. And vendors have accomplished this in a number of different ways. Some vendors have DC motors where if they lose the home position, they just engage the battery system and run the blade pitch till they go home. Others use more sophisticated methods to figure out where they are if they lose the feedback solution. So in the blade pitch application, just to summarize, there's two approaches, absolute and incremental, and we believe incremental is more durable. And we'll talk a little bit later about some features about incremental encoders, about how you can get a more reliable incremental encoder as well. We also believe putting the encoder behind the motor is more durable, particularly when you talk about that small encoder with a small bearing hooked to a big plastic gear. It's just really vulnerable versus that durable solution we showed you earlier where it's mounted behind the motor. So let's talk about the slip ring. Well, what's the slip ring for? Again, optimizing energy output, monitoring the gearbox. Some companies actually even use it to quiet the overall operation of the blades. So here's a typical slip ring encoder, and you see right away this is a very small and relatively fragile component. Again, typically an optical encoder. It's very vulnerable to dirt and dust and vibration and shock. And you also see this got a pretty sophisticated mounting system, and you're coupling it. So there's a lot of reliability problems that you can have with that. Typically, all optical encoders can have issues with optical sensors. They can have current problems, shaft current specifically, and they can have bearing problems. So ideally, you want to try to attack and eliminate each one of the problems. You want to, wherever possible, eliminate bearings in your design. You want to eliminate couplings in your design. You want to eliminate complicated machine parts and make assembly just easy and tolerant. And you want your design extremely temperature tolerant. As all of you know, there's just enormous temperature extremes inside the nose cone. So let's take a look at a real-world solution here. So on the left, you take a look at this picture here, and we're showing a slip ring assembly. And you see on the left-hand side of that picture, I've highlighted in red that here's that encoder that you saw before, but now you're looking at it from the side. And it's coupled, actually, to the slip ring assembly. That's an optical encoder with a lot of complicated mechanical and glass parts. Instead, what you can do is use a simple magnetic encoder, for example, this model, and you can see this has got some really simple construction mechanically. It's got a ring on the outside, and then it's got the electronics in a potted brick in the center. This gives you some real incredible durability because now you're not using encoder bearings, you're not using couplings. It's directly mounted on the shaft assembly, and it's all potted in plastic, so it's really, really resistant to temperature. It ignores oil, water, and grease. So how do you get there? Well, we start out, and we'll just show you a little zoom in on this slip ring assembly, and now we've seen the encoder assembly here. What you do is remove that encoder assembly and its little holding assembly, and now what you do is you add that rotor that you saw to the existing screw holes. You add the stator assembly. And now you've got a solution that basically fits in a lot less space than the existing slip ring encoder, but provides mechanical interchangeability, electronic signals that are compatible, and going to give you an incredible increase in reliability because it's basically a disc spinning in front of a sensor now, not this complicated set of plastic, glass, bearings, and so on. So you can retrofit this to in-the-field units. You don't have to modify your slip ring. You can use existing bolt holes. And this is going to survive temperatures easily -40 C and below and up to 100 degrees C. It's also electrically protected from damage. A lot of low-cost encoders don't use regulators like they should. Ask your encoder vendor, are you using voltage regulators around the entire encoder? You'll need an automotive grade quality because you're seeing surges on the line. You're going to see induced voltages that aren't from the encoder. They're from the drive or other things, and they're going to kill your encoder, or for lightning, from that matter. So now let's take a look and go to the backup generator application. So here you have a typical 1.6 megawatt generator. And you've got a lot of vibration, you've got a lot of shock. So what can you do? Well, there's a couple of different solutions that you can implement to solve your encoder problems. I'm showing a no-bearing solution on the right-hand side. And this is in our world, this is the ideal solution. Again, there's no couplings, there's no bearings, there's nothing to wear out, there's no glass, nothing fragile at all. This is bolted straight to the generator, and the rotor is bolted directly to the generator shaft. Some people, hey, they don't have that sophisticated, well-machined back of the generator. You're dealing with a relatively crude design mechanically, or your tolerances just aren't that great on the back of the generator. So now you can still go with a hollow shaft design that clamps on the shaft. But again, you can use a magnetic sensor system on this type of encoder that's going to offer a huge improvement in reliability because, again, magnetic sensors aren't affected by dirt, dust, and oil the way that optical sensors are. So I've spent some time bashing optical encoders a little bit, and you're probably wondering, well, what's he talking about? Why is he not, a big fan of optical encoders? He said at the beginning of this presentation he sells optical encoders. What customers can buy those? Quite frankly, optical encoders were originally designed to be used in machine tool type applications, ones where the temperature was controlled. So when you put them out in the real world, in outdoor applications, you get a lot of temperature fluctuations. And we'll talk about why that's so deadly to optical encoders. So how does an optical encoder work? Again, for those of you that are encoder gurus, I apologize. We'll just give you a little basic. You're shining an LED. You've got a disc with lines written on it or holes punched through it. And on the other side, you're watching that light with a phototransistor or photoreceiver, and you're making pulses or counting proportionally. This is how an optical absolute encoder works. This is also how an optical incremental encoder works. So what can go wrong? Well, a lot of things. Left-hand side, you can have bearing failures. Your couplings are definitely vulnerable. You see on the right-hand side, those are some optical discs, and if you look at the one on the left, boy, it's pretty hard to see through those little holes. Dirt got inside the encoder, some dust. And in the right-hand picture, you see a chipped glass disc, and that's definitely going to cause you to get the wrong counts out of that encoder, cause a drive trip, and before you know it, your wind turbine is shut down. And both of these are all real-world pictures that we took from real encoders removed from real applications. So from the encoder world, traditionally, the defense was to argue, oh, I have better IP seals. I'll get a better IP-rated encoder. That's the key to the whole success of encoders, is to get a better IP rating. And so manufacturers really engaged in an arms race to increase the IP rating, the sealing rating of their encoders. But here's the truth. The truth is that no matter what IP rating the manufacturer claims the encoder is the day they ship it to you, it changes, because you have rotating shafts, rotating seals, and those wear, just like a motor, just like any other application. And as those seals wear, what happens is the encoder can no longer withstand pressure changes that come from those temperature changes I warned you about. So we ship you an encoder with nice factory air in it at 20 degrees C. Then you get it hot. That air wants to get out. Eventually, it exceeds the pressure capability of the seals. The air comes out. Now you cool the wind turbine down at night to -10. You've got a vacuum. It draws in air, but unfortunately now that air's got dirt, dust, water, and other contaminants in it. Now your optical encoder can be blinded by those things. Absolute optical encoders have these problems in spades, honestly, because they have multiple sensors, so that any one sensor that goes wrong, they have problems. Optical absolute encoders also are more precise, and so any slight flaw cannot be overlooked by the sensor. It'll often give you a position error. You often have plastic gears and couplings inside these encoders. So why is a magnetic encoder solution more reliable? Honestly, when you look at these magnetic encoders, the big benefit is the no bearing design. That is, you can mount the encoder, as I showed you before, directly on the motor, directly on the assembly, and take advantage of those big, huge bearings you've got in the generator or motor instead of using tiny little bearings in the encoder. So how does a magnetic encoder work? Well, typically you've got a Hall effect or a magnetoresistive sensor, some sort of thing that can detect changes in magnetism that's placed in relatively close proximity to a magnetic rotor with poles written around it. The great thing about magnetic encoders, obviously, is magnets work in oil and water and dirt and dust. So when you think about a no-bearing encoder, it doesn't matter that there's oil or grease or other things penetrating this. So now the whole IP rating housing game isn't important to you anymore. The encoder, as long as it doesn't mechanically abrade something, you can have contaminants, you can have oil, you can have water inside that housing that's still going to work, because the sensors are fully potted in a brick of plastic. So what if you can't use those? I touched on this before with the generators. Perhaps you don't have a precise assembly. Perhaps you don't have a flange. You can't use a no-bearing encoder. It doesn't prevent you from using magnetic encoders in your wind turbines. That is, you can use a hollow shaft encoder. And a hollow shaft encoder can be added to the back of a brake assembly. It can be added to a generator. And it can also often be used, both styles can be used to retrofit existing encoders. So even if you've got these in the field and you're suffering a lot of failures, like we have seen in a lot of customers, where they're just suffering with a lot of optical encoder failures, they say, well, what can I do? You say you can install a magnetic encoder and fundamentally retrofit these machines, but without huge mechanical modifications. So here's some shapes and sizes of magnetic encoders. I just threw some pictures up from Avtron in particular, but there are vendors across the world that make heavy-duty encoders. And again, I'm focusing in, for these type of applications, we really strongly favor the magnetic encoders. Remote monitoring and diagnostics is another important area. It's really important to know what's going on with your encoder. A lot of times you have a drive trip or other issues that says you've got an encoder fault, but do you really have an encoder problem? You'll have a guy climb the tower with an encoder strapped to his belt. He replaces the encoder. He's still got the drive fault. Now you got to chase the real problem, which might be a drive input card or wiring or other issues. A lot of these modern encoders now, they come with a digital signal processor inside the encoder, so they can provide two levels of diagnostics. They can give an LED to the guy in the tower, but more importantly, they can give a remote diagnostic message before you climb the tower, so you'll know what's going on. A lot of people treat encoders like unknown little black boxes, and so this type of diagnostics really changes that dynamic, and you say, I either trust that encoder, it's working well, or I know I need to replace the encoder. So when you're looking at maintenance, how can you avoid causing more problems? How can you prevent things from going wrong? Number one, particularly if you've got optical encoders, you're going to need to treat them more gently than almost any other component. You can't strap them to a guy's belt and bang them up a 100-foot or 300-foot tower. You've got to treat them pretty carefully and keep them in factory packaging before you install them. You can't strike them or drop them. If you're replacing an encoder, make sure that you replace it with all the existing hardware. Some encoders aren't protected well from shaft currents, and so for these types of designs, you want to make sure if the encoder came with little plastic washers or other insulators, you're definitely going to want to keep that stuff in there. I know it looks like weak claptrap, but it's actually an essential part of the design of that manufacturer. What I hope is that you can find a manufacturer you can move to a design that eliminates a lot of those small, weaker parts. But if you're stuck with a manufacturer and you're committed that direction, keep replacing all the little bits, because if not, you're going to accelerate your failure rates. Avoid unnecessary replacements. Again, a lot of people don't trust the encoder. They fundamentally learned there's a lot of encoder failures on wind turbines, so the first thing they do is rip the encoder off. The problem with this approach is it often masks other problems. You may have wiring problems, you may have voltage surge problems, you may have drive input card problems. Often, if you're having a lot of problems, try to get one of those diagnostic encoders in place of the non-diagnostic styles, put them in there and see if you can really figure the problem out. Also try replacing encoders with more durable models. Go upgrade from optical to magnetic, upgrade from a model that doesn't have regulator protection to a unit that does, and so on. So stepping up can then help you avoid unnecessary replacements. So what can encoder vendors do to help you improve reliability? Encoder vendors can give you an assessment either of your existing design, or if you've got an existing installation, you should be able to get your encoder vendor to climb the towers with you, to assess your spares usage, to look at what's going on and say, how can we fundamentally improve this problem? Encoder vendors can provide recommendations. They're happy to. They'll look over what you're doing and give you their best advice on these areas. Support. We believe encoder manufacturers should provide great support. Avtron in particular is committed to 24/7, 365 technical support, where you can call our company any time of the day or night, and you can reach a real engineer that knows encoders and will answer your question. That's from anywhere in the world. We do support multiple languages, so it's really a matter of being focused on supporting the customer, because we know it may be 2 a.m. when you've got a problem and you need support. So expect that from your vendor. And again, diagnostics, diagnostics, diagnostics. We've talked a little bit about this enough. So if you look at real-world MTBF, Avtron actually has tens of thousands of these units on blade pitch units all over the world. We've got units on generators and so on. And Avtron has measured our MTBF, our mean time between failures, and we have a 4.5 million hour MTBF on blade pitch applications. You say it's crazy. You do the math, figure it out, it's 500, 400 and some years. That can't possibly be true. We're not talking about how long the encoder lasts. We're talking about how few fail. How do we get there? Well, in this particular application, we're talking about a no-bearing magnetic encoder installed behind the motor, between the motor and the brake. It's incredibly well protected. You can't hit it. You can't drop it. It's bolted in place. It's a solid piece of aluminum. It's got a disc spinning inside it. Mechanically, there's very little that can go wrong, and electronically, it's protected. So it is possible for encoder vendors to give you a solution that's going to dramatically increase your reliability on the blade pitch, on the generator, on the slip ring, the yaw. All these are possible, and this is proven in the real world. It isn't somebody sitting calculating that this could be a potential MTBF. This is real-world calculations of in-warranty issues versus installed base and how many hours it's running. So again, Nidec Avtron Automation, this relatively new company from 53 or 50-some-year-old company from 1953, and we look forward to helping you improve your wind turbine performance. Let us know how we can be of assistance to you. With that, I'm going to turn it back over to Paul for questions.
All right, thank you very much, Brian. You know, as a mechanical engineer, I always enjoy discussions of electrical products. I always feel like I'm learning something. So let's start answering a few questions here. And ladies and gentlemen, please recall that little white box in the screen to your right is where you can start typing. All right, we have some questions already, Brian. Here's one. Which of the encoder failures you outlined do you consider the most serious?
I'd say probably most serious is the failure of the blade pitch encoder. At the very worst, it causes your blade pitch system to shut down, go into safe mode, and immediately force the shutdown of the tower. But as you saw early in my presentation, those blowdown examples of where the whole tower has been blown down, and these are examples of where if you don't know your blade pitch position and you either lock the rotor or you're in excessive wind conditions, you're going to lose your multi-million-dollar tower, and in fact, obviously, it's extremely dangerous to people. So I'd say that's probably the number one thing, Paul.
Okay, very good. Thank you. There's another question. With all the encoder-related failures out there, why isn't anyone doing more to eliminate them?
I'll tell you, I ask myself that question a lot, honestly, Paul, because I look at encoder manufacturers, and a lot of encoder designs that we're using today are 30 years old. They're 40 years old. They're the same thing that they mounted on the back of a Mazak machine tool in 1970. It's amazing. I think it's a combination. Manufacturers use designs they're comfortable with, ones that they're familiar with, so they may copy something that they saw on a control design. And then there's another factor, and that is I don't think that the manufacturers fully always feel the pain from the very end user's downtime in a direct way. A lot of times we've got service companies and other people in the middle that are really feeling the pain. So my goal here is to kind of bridge that divide and say, users, we feel your pain. We can get your, as encoder manufacturers, we can really get your reliability up. Designers and manufacturers, hey, we can help you to produce a more reliable design. This tiny little electromechanical device, and Paul, you pointed out you're a mechanical engineer, but an encoder is kind of a never land. It's mechanical. It's got gears or pulleys or hookups, but it's also electrical. So no one's really sure whose device it is. By the way, they're always saying, well, somebody's. But again, by bridging the divide, our goal is to try to get manufacturers, designers, installers, and end users in a place where they really see fundamental improvement in that reliability.
Okay. Well, let me ask a question. I say one of the pictures you showed was, I think it was a green LED on one of the encoders as a diagnostic device. How would you use that? Wouldn't you have to hook up a voltmeter or something?
That's a really good question. The LED in this case is a pretty sophisticated indicator of what's going on. That particular encoder I've shown there actually has a digital signal processor inside of it. So what it's doing is analyzing, can I see the sensor? Are things moving the way I expect? Can I produce a good quality signal? In this case, that particular encoder I showed is an incremental encoder. So the digital signal processor is measuring, am I making a good quadrature signal? Is A leading B by 90 degrees? Is everything happy? If all those things are true, you get a green LED. Mm-hmm. If those things aren't true, now you get a red LED, get a remote alarm contact. It gives you a foundation under which now the person can begin to troubleshoot the encoder. But the simple fact of a green LED is far more than a power light in this device because it's actually self-diagnosing all the time.
I see. Okay, tells you that you can look somewhere else for the problem if the green light is on. Okay.
Exactly, and again, it's a foundation of trust because most people because they've had so many encoder failures, they don't trust the encoder. Now they can.
Okay. All right, ladies and gentlemen, I want to encourage you to write to ask questions of Brian. He's not going to be here forever. Brian, I'll ask you one more here. What one simple thing both OEMs and end users can do to reduce encoder failures?
I would say the number one thing that both OEMs and end users can do is to actually focus on encoder reliability. I know that sounds like oversimplification, but by focusing on it, when you measure what gets measured, gets done. So as a manufacturer, if you actually go back, ask your service force in the field and say, okay, what % of downtime incidents were related to encoders? For end users, again, how many hours are you losing in the field to encoder-related control system downtime? Now by measuring that, you're going to be able to decide, is this a big thing for me? Should I be taking action? Or is it a small thing? And we think, our experience in wind turbine farms and OEMs across the world is when they measure it, boy, they find some huge areas of improvement. Then they can look at practices, improvements, designs, retrofits, whatever it takes to improve that reliability.
Okay. All right, Brian. So finally, the audience has really popped up here. Let's see, a couple of the questions here. GE BAA troubleshooting for a GE pitch system suggests checking blade positioning and then unplugging the encoder for 15 seconds, then replugging it to see if values stay the same. Does this help verify that the encoder is bad? Any other solutions would be helpful.
That's a good question. The GE is probably the right people. You should be reading the GE Diagnostic manual for the full procedure on this. I have some familiarity with the GE blade pitch system, however, and so I understand what the goal is you're trying to verify when you plug and unplug whether or not you're achieving correct encoder connections. Again, on those systems, I think the GE procedure is correct. They're leading you through the basics. You can also, in a lot of situations, again, once you've measured the wind, GE allows you to attach a pendant and do a manual jog of the system, and that's going to tell you whether your encoder feedback system is telling you the truth, because you can actually watch the gears move slightly, and then you can obviously verify with the handheld pendant that the encoder counts have matched.
Okay, very good. All right, here's a question from Dennis. How about failure from lightning? How can this be mitigated?
That's a really good point. Lightning is a big killer in wind turbines of everything, drives, controls, and so on. So part of the combination is encoder manufacturer design. We include some features, or should include some features, that help you suppress lightning. That we should provide you with information about testing to certain voltage levels and so on. Then on the flip side, the manufacturer and installer needs to make sure that proper grounding is really essential, because you're not going to avoid the strike, all you're going to do is try to pass it around all these sophisticated control systems. So from a manufacturer's point of view, you want to make sure that the vendor has put good regulators in his encoder so he can withstand these external voltage surges that come with lightning. They should be able to withstand short-term, very high voltage surges, and they should have designs that are externally grounded but don't hook the housing ground to the electronics. That's a great flaw in a lot of these designs. Some people use capacitors and other things to try to suppress noise. You don't want that. You want your board sitting in your encoder all alone in a nice little Faraday cage is the term that we learned in college, and you don't want that touching anything that's associated with the ground system. Now you've got the housing mechanically and electrically grounded, so now high voltages that are induced from lightning are discharged through the tower into ground.
Very good. Okay. Right, that's another question here. Is it more common for the magnetic rotor or the encoder itself to go bad? We are replacing the M56 version with the AV56 model. Any possible TS methods to verify which is the problem?
That's a good diagnosing question. When you look at the encoder, quite honestly, the magnetic rotors are almost impossible to kill. If you look at a magnetic rotor, it's magnetized in what they call a hard magnetic material, not physically but magnetically. It's very, very difficult to demagnetize these types of rotors, and that's true, of many vendors. So you can start out with the assumption, for the most part, unless you've got somebody swinging giant magnets around, you won't demagnetize your rotor. It's pretty darn hard. So you're probably going to focus on one of two solutions. You're going to focus on, are my electronics good? Or in other cases, is my rotor aligned properly to the sensor? Because if you don't have the rotor in the proper position, obviously the sensor can't see it. So for designs that use a modular design, you want to make sure you follow the manufacturer's recommendations about aligning the rotor to the stator.
Okay, Jim has a question here. Common problem we have seen on pitch motor encoders is the loss of pulse count. What aspect of an encoder can help prevent pulse loss and make the encoder more robust?
Yes, that's pitch. A loss of pitch count really is, I'll call it the symptom, the overall symptom of the problem. The real problem is hidden underneath, and that is the encoder is actually failing you in one or several ways. The first thing you probably want is an encoder in there that's got some diagnostics, so it can tell you if it's healthy or not. That would help you right away to figure out, oh, is the encoder guilty? Is it happy? Or is the encoder got issues? If the encoder says it's happy, now you're chasing other issues. You're chasing wiring issues or chasing card diagnostics on the receiver end. If you've actually got encoder issues, now, honestly, for most encoders, you can't take them apart and decipher them yourself. You're going to rely on your encoder vendor, or if you're not happy with them, find a new one, find a competitor, and say, hey, I've got 3 of these encoders on my towers that keep losing counts. What can you do about it? And give them an opportunity to either view them in sight, malfunctioning, or ship them to them. Manufacturers are always eager to get business, so they'll help you try to decipher, what is the flaw in these existing designs and how can they help you overcome it.
Okay, excellent. All right. Ruben has a question here. Is a good one. How can we maybe resist encoders for humidity? I think you must protect encoders from humidity, salt, in applications close to the sea.
Very good question. The truth is, for an optical encoder, there really isn't a good way to protect them, which is why Avtron's not very. We try to avoid selling our optical encoders for wind turbine applications. Magnetic encoders, on the other hand, you can make some big steps of improvement. You may recall earlier in my presentation, there's a picture of some potted electronics in a brick of plastic. That makes an enormous difference is to get a potted design. Avtron and other manufacturers make potted and unpotted designs. Ask the manufacturer, can I get a potted version of this? Can I get an encoder that the magnetic parts are all potted in a brick of plastic? Now you're really invulnerable to humidity, to salt, to all those things, because I'll call them the tender parts, are all inside that very secure piece of plastic, and it's not going to be affected.
Okay. All right, here's one from Jay. He says, what drives the specification of resolution for wind turbine mounted encoders?
Insanity. Actually tradition. Various vendors with their control systems put resolutions of encoders on their feedback systems. But honestly, for blade pitch systems, almost everybody has a lot more counts than they can ever possibly use, because most people are actually measuring counts or position behind the motor. The motor might have a 27-to-1 gearbox between the motor and the movement of the blade, so for every revolution of the motor, you only see a tiny amount of degrees of change in the actual blade. So a lot of manufacturers honestly have a lot more resolution than they need. I've seen the classic design is the German one with an absolute encoder with 8192 counts behind a 27-to-1 gearbox trying to measure a blade pitch to about 1 degree. You've got an awful lot of counts there to try to measure 1 degree. It's really overkill.
Yeah. Okay. Kyle asked a question here. How sensitive is a magnetic encoder to EMI?
Very good question. There's two kinds of EMI that can affect encoders and magnetic ones, but I'll go through both of them. The first kind is external magnetic fields, the M in magnetic, and that is brakes and other devices, the motors, generators that generate magnetic fields. And so what manufacturers do is they pick a combination. For instance, Avtron picks a combination of sensors that are angle sensors rather than magnitude sensors. So external fields can be readily ignored because they come from the wrong direction than the rotor. We can tell the difference between the rotor and the world outside. The second thing on magnetics is that most manufacturers who do magnetic encoders provide some forms of shielding. It's similar to an electrical idea, but you're routing the magnetism from external fields around the encoder. So in that example that we saw where the encoder was sandwiched between the motor and the brake, you're shielded from those powerful magnetic fields coming off the brake. Now on the electrical side, the E of EMI, now what you want to do is you want to have a design that's actually got a Faraday cage built in. For Avtron, we actually take the circuit boards and wrap them in copper foil. It's extreme because we want to make sure nothing can get in. You can have some extremely powerful radio wave fields examples. We were familiar with an example where a manufacturer actually installed some wind towers north of a aircraft radar installation, and they could actually see the radar towers from where they were installing the towers. And when the tower was pitching directly into the thing, they could actually jam the drives. If the door was open to the drive cabinet, there was so much E pouring in that the drive couldn't think. So you need to make sure you're very effectively shielded from both magnetic and electrical interference.
Oh my goodness. Jim asked a question here that I think is similar to the last one. He says, what design features make one vendor encoder less sensitive to pulse count loss? Pulse count loss is the question, compared to another. Shall I read it again?
Yeah, that's good. I think that's a really good question. And it's not just always the vendor, it's the fundamental design. But I can say that in general, what you want to focus on is reliability, because reliability is how you're going to keep your pulse counts. So you want an encoder that isn't going to fail if you get dirt and dust on it. You're going to want an encoder that doesn't fail if you get salt water on it. You want an encoder that won't mechanically fail, that the gears won't wear out, or you won't end up with a shaft coupling breaking and so on. All those things are essential to making sure you don't lose pitch count. So when you push the manufacturers, generally what you're talking about is most manufacturers talk about duty, heavy duty, severe duty, and so on. Now, quite honestly, there's a huge disparity between manufacturers as to what heavy duty really means, but what you're doing is trying to ask that manufacturer, what's the better thing you've got? What's the more durable encoder that you've got? And if they say, we're selling you our best, then shop for another vendor, because there are people that make extremely rugged encoders. I mean, some people call a heavy-duty encoder something that weighs 4 ounces, and some people, like Avtron, call a heavy-duty encoder weighs 16 pounds. It's just, there's a huge spectrum. So pick a vendor, push them, and try to push them for increased reliability.
Okay, very good. Hey, Carlos asked a question. What's the resolution that magnetic encoders are offering?
That's a good question. It varies on the vendor. For example, Avtron out of the gate offers somewhere between 3,072 counts per revolution all the way up to about 5,000 counts per revolution on most of our models. Most people don't ever need or use those kinds of resolutions. More commonly is 1024 pulses or 2048 pulses per revolution. Nice binary numbers left over from the 1970s that, again, control engineers have been using for many years. So magnetic encoders, by and large, can reach the resolutions that are required and honestly quite beyond what's really needed.
Okay, very good. Dennis asked a question here. He wants to know, do you have any experience with fiber optic encoders which are electrically passive? He says both magnetic and optical encoders incorporate electronics.
Yes, this is an interesting part of the market. These actually didn't start in wind turbines. These designs actually started in places where it was too hot to try to run electronics. And the idea is you build an optical encoder at a distance. You shine a light through a fiber, and then you pass it through the disk, and then you watch it with another fiber, and then you run that fiber all the way back to a photoreceiver. The problem is that it's 8 times more vulnerable than an optical encoder, because at its core you've got an optical encoder that's very vulnerable to temperature changes, cycling, water, dust, and dirt. Wherever you tried to hide it in the wind tower, it's still going to see a lot of problems. And then you've got these fragile fiber optic cables, and unfortunately fiber optic cables are very bend limited. There are a lot of issues with fiber that make it quite vulnerable, even the plastic fibers. And then on the other end, now I've got to make that little fiber disk fiber trick work optically, so if I get any dirt or dust in that piece. So unfortunately, although they look really cool and reliable, and boy, I'm not going to have any electrical parts up in the part of my tower, what they really are, unfortunately, with present designs, is less reliable than an optical encoder.
Okay, very good. And here's our last question from Rod. It's a true and false question. He says, we were told that the magnetics of the rotors in the M56 version and the AV56 version are different and not interchangeable. True or false?
That's a good question. Depends on the model. I know that's a weaselly answer, but you have to go back to the manufacturer. You have to go back to Avtron and give them a part number and say, this is the 56 I've got. This is the AV that I'm replacing it with. Are these interchangeable? You need to exactly check the part number. It's not a good general statement. So I'll say partially false.
Okay. All right. Well, that was our last question. And we're running out of time, too. So, ladies and gentlemen, I want to thank you very much for your attention. Once again, this webcast will be available for reviewing at windpowerengineering.com. One final message. You can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. This concludes our presentation. I'd like to thank everyone for their attention. From the staff here at Wind Power Engineering and Development, we wish you a good and productive day.
Thank you, Paul.